probably seen him around campus or on the soccer field. But I'll tell you his whole life story. I don't know his whole life story. So Sergey got his bachelor's and master's degrees in geology and then in geochemistry from Novosibirsk State University. And he also got a PhD there in 2012. As a PhD student, he actually came to Geophysical Lab to start doing some diamond cell research. But his PhD was also using diamonds, but in that case it was studying the defects in diamonds, how they move around. He had some papers on natural diamonds, some on synthetic diamonds. He traveled in the summers to near the Arctic Ocean to pick up diamonds and study them. So then in 2012 he came here and has studied many things. He'll tell you about the lower mantle minerals he studied, but he also used the same sort of techniques to study hydrocarbons, to study new chemicals of magnesium and oxygen, and he even put diamonds inside diamonds. He's so into diamonds that he squeezed on a diamond inside a diamond to see what would happen. And you can read that paper too. In addition to all the great research he did here, he also helped us win the past 2 mud cups. He also tied in 1 mud cup, and there was 1 other mud cup he played in. We don't need to talk about that one. He's hosted beer hour many times. He got married last year while he was a postdoc, and he stopped hosting beer hour after that. But continues to do great research. And today he's going to tell us about these lower mantle minerals and some innovative and really impressive experimental work and some of the ideas he has about how those experiments teach us about the core mantle boundary and the lower mantle. Take it away, Sergey.
Oh. Thank you, Zach. Can you hear me well?
Yes.
I guess you are. Well, I've known Zach for 3 years, and ever since he couldn't pronounce Novosibirsk correctly. So I want to just start by saying a few words why am I using optical absorption as a method. So recently in the Geophysical Lab, we have developed a very new method to study optical properties of materials, not only at high pressure, but also at very extreme temperatures up to several thousand Kelvin. So, and it is just natural, in my opinion, to use these methods in application to lower mantle minerals. So just to look what their color is at such high pressure and temperature. So, and the region of the Earth that we're most interested in is the lower mantle. And in the lower mantle, we just have 3 minerals, so the mineralogy of this region is very simple. However, these minerals are squeezed to a very different range of pressure and temperature conditions there. So, and probably this is the reason why we have such complex geology near the core mantle boundary. You can see that there are a lot of processes going on here. So the argument that I will try to make today is that optical studies can tell us something about the physical properties of these 3 minerals. And from that, we can extract information that can be used in geodynamic modeling so to understand what's going on in this region. My tool of choice is a diamond anvil cell, and most of you are probably familiar with this method. But just to put you a little bit in the context, so basically what we're doing is just squeezing on a material that's sitting between 2 diamond anvils, such as shown here and here. And our sample is usually surrounded by a pressure medium. So this is really all you need to know. This method allows us to generate pressure and temperature conditions that simulate the pressure and temperature conditions that are inside planets. Here, for instance, you can see the PT ranges that can be generated by, say, resistively heated diamond anvil cells, double-stage diamond anvil cells, and multi-anvils, and then laser-heated diamond anvil cells. So laser-heated diamond anvil cells is really the tool of choice if you are to study deep planetary interiors such as Earth's core or Earth's lower mantle. And this is why I use this method. So, but generating pressure and temperature is one thing, but probing materials at such conditions is a whole different story and represents itself a great challenge. But we're after that challenge. So optical studies, optical spectroscopy is a very mature technique, and in fact, it has been one of the first methods that was applied to studies of minerals in diamond anvil cells. So here is just a simplified setup of how our optical absorption experiments look like. So you have a light source that emits some light, some white light onto the that illuminates the sample with white light. And then you collect the transmitted portion of this radiation by a detector of sorts. And then you just compare this transmitted light through the sample versus against the transmitted portion of the light collected through the pressure medium. And basically using this decimal log, you get a what we call an absorption function, or simply a spectrum. So here is an example of an optical absorption spectrum of post-perovskite at 130 GPa at room temperature. So just for those of you who don't eat absorption spectra for breakfast, I want to point out that here we have, so we usually plot this absorption spectra in wave numbers. But anywhere from 12,000 wave numbers to 25,000 wave numbers, you have the visible range. And below 12,000 wave numbers, you have infrared range. So you can see here that we have a spectrum that has several absorption features. And from the position of the absorption bands, you can say something about what is the electronic structure of iron that's sitting in this mineral. And from that, you can say something about its spin state. And spin states of minerals, of iron in minerals, affect the physical properties. So therefore, knowing the spin state of a mineral as a function of depth in the Earth, you can say something on how its physical properties change as a function of depth. And then you can use this information in geodynamic modeling. However, the overall opacity, the overall absorption level of this spectrum tells us something about what we call radiative thermal conductivity, which is one of the two microscopic heat transport mechanisms in minerals. So radiative thermal conductivity adds up to the total thermal conductivity, which then again is a crucial quantity to use in geodynamic modeling. So this is how optical studies, in my opinion, can contribute to geodynamic modeling. But you may argue here that the lower mantle is not at 300 K, of course. And we would like to collect absorption spectra not at room temperature, but at high temperature. And here is a problem. So once you heat your sample to temperatures of above 1,000 Kelvin, well, doesn't matter what temperature, but you will get intense Planck body radiation. And the hotter you heat your samples to, the more intense the radiation is, and it also moves towards the visible range. So at hot temperature, at some point, your Planck radiation will dominate the signal, and you will end up having a very poor signal to background ratio. So therefore, this method hasn't been really used at temperatures above 1,000 Kelvin. And that's our solution to this problem. So at the heart of the solution lies what we call a supercontinuum, or simply a white laser that has a continuous wavelength distribution from 400 to 2400 nanometers. Importantly, it is a pulse source, and we can time it in principle as we want. But what you have to remember here is that the pulses are really short compared to the duration between the pulses. So in this particular case, we have 4 microseconds. 1 microsecond is a millionth of a second between the pulses. So we take an electrical output of one of the pulses as a trigger for the heating laser. So we heat our samples for just 1 second. And 200 milliseconds into the laser heating pulse, we start opening the detector, our gated detector. And we do it in such a way that the gates of this detector overlap exactly over one of our supercontinuum pulses. So, and we do that for half a second. As you can see, 500 milliseconds is half a second. So we collect a bunch of supercontinuum pulses in just one collection, in just 1 second. And altogether, this method allows for very short accumulation times compared to just regular conventional optical spectroscopy, and gives us an excellent signal to background ratio at high temperature. And I do have to say here that we have recently published, although we have recently, excuse me, I do want to say here that we have published this technique recently. And although I'm the first author on this publication, I do want to say that Nick and Alex are really the people who stand behind and should take most of the credit for this technological development. So we have a tool that allows us to look at to do optical studies of minerals at high pressure and temperature. So what are the problems we apply this method to? So the first problem I want to discuss is iron spin state in the mantle. And our long-term goal here is to reconstruct the spin state of the mantle as a function of depth. So a few words about what spin transitions are. So consider an Fe2 plus ion sitting in an octahedral oxygen environment. So oxygen, the electrostatic repulsion of oxygen p electrons on d electrons of iron will be such that the d electrons will split into two energy levels, the T2G and EG level. And the energy difference between the two levels is termed crystal field splitting energy, or simply delta. So the Hund's first rule governs the distribution of electrons among these orbitals, such that you end up having 5 electrons that have a spin-up orientation, and then the 6th electron with a spin-down orientation here. However, you can apply pressure on this system and effectively change this delta. So basically, you can think of squeezing onto these oxygen atoms. As they come closer to iron, they will cause more electrostatic repulsion on the iron d electrons, and as a result, delta will increase. So you will increase the separation between the T2G and EG levels, and as a result, at some point, delta will become larger than EP, and that's the moment when the Hund's first rule doesn't work anymore, and your EG electrons basically jump down to the T2G level to pair with the d electrons that are already sitting there. So that's what we call low spin configuration, and this is what we call high spin configuration. And this kind of transition is what we call a spin transition. So traditionally in mineral physics, there have been two methods to probe pressure-induced spin transition. So the first one is X-ray emission spectroscopy. The second one is Mossbauer spectroscopy. Both of these methods require high fluxes of X-ray photons, and therefore they're mostly combined with synchrotron-based sources, X-ray sources. So this is one of the disadvantages of these two methods. Another disadvantages are that they are very difficult to combine with high temperature. Most of the X-ray emission and Mossbauer studies are limited to room temperature. Also, X-ray emission spectroscopy is not a site and valence specific technique, which means that if you have a mineral which has several different iron configurations, valence or coordination configurations, those you won't be able to distinguish between the spin transition at these sites with the X-ray emission spectroscopy technique. Mossbauer spectroscopy is a site and valence specific method. However, the interpretation of Mossbauer spectra is very complex, and therefore we don't, well, in other words, we don't have good references for how low spin Fe2 plus and Fe3 plus iron should look like in Mossbauer spectra for crystal chemically complicated minerals. And instead, I propose to use optical spectroscopy. And the reason optical spectroscopy works well is simply because the energy difference between the T2G and EG level usually lies in the optical range, which means that you can shine white light on your sample, and that white light will excite an electron from the T2G level onto the EG level, and that will give you an absorption band in the spectrum. And then you can use the energy of this absorption band, its spectral position, to say something about what is the electronic structure of iron in the mineral that you're probing. So, however, the question to address is, what are the signatures of low spin Fe2 plus and Fe3 plus? Because this method has been heavily, in my opinion, underused in probing spin transitions in minerals, and therefore we really need to know how do we actually know when we're looking at low spin Fe3 plus at high pressure, for instance. So this is the question to ask. So the way I approach this problem is what I'm going to talk about now. So here is the crystal structure of ferropericlase, the second most abundant mineral in the mantle. The crystal structure is pretty simple. It has only one cation site for iron. This iron is mostly Fe2 plus. However, low mantle ferropericlase usually has some amount of Fe3 plus that complicates the matters quite substantially. So ferropericlase has a well-documented spin transition at room temperature. It's believed to be low spin at pressures of about approximately 60 GPa. So what I want to say here is that I propose to use models of I propose to use other minerals as sort of models of the low mantle minerals. And here, siderite, in my opinion, can be and that's what I will try to convince you, can be used as a model of ferropericlase. And the reason to that is simply because siderite contains exclusively Fe2 plus that also sits at an octahedral site, just as in ferropericlase. But most importantly, siderite has an optically apparent spin transition. So here on the left, you can see optical photographs of siderite as a function of pressure. And basically, as you squeeze on your mineral up to about 45 GPa, nothing happens to its color. It remains transparent. But once you hit 45 GPa, excuse me, you get an intense green color, and that readily tells you that something's going on with its electronic structure. So, and of course, such an apparent change in color must be recorded in absorption spectra, and that's what I'm showing you on the right. So the high-spin siderite has only a weak absorption band at approximately 14,000 wave numbers that I marked by 1 here. However, low-spin siderite has a more intense absorption band at 16,000 wave numbers. And this absorption band is actually characteristic of low-spin Fe2+. Also, you can see a dip in absorption at green wavelengths, and this is exactly why this mineral turns green upon the spin transition. So we do understand these absorption bands in terms of spectroscopic selection rules. So the selection rule that we're mostly interested in is the so-called multiplicity selection rule, which basically states that upon the excitation process in your mineral, or any material, in fact, the multiplicity, or simply the number of unpaired electrons, should be preserved. So you can count unpaired electrons here. So 1, 2, 3, 4. We excite this electron from the T to G level to the EG level, and we end up having 4 unpaired electrons again. So this is a multiplicity allowed optical transition that gives us an absorption band. So only allowed transitions theoretically should give intense absorption bands in the spectra. We can now plot this multiplicity allowed transitions on energy level diagrams, and this is just one example for D6 elements, and Fe2+ ferrocyan is one example that obeys this diagram. So what you see here is just basically 2 energy axes, and you can think of this, of the horizontal axis, as of pressure. You can see that this diagram is divided into 2 parts. The high spin part that has only one oblique green line, and oblique green lines are multiplicity allowed excited states. The horizontal green lines are the ground states. And you can see that in the low spin D6 configuration, you may have several excited states, while you have only one in the high spin state. So the important thing to say is that all minerals that contain D6 metals in their structure that sits in at an octahedral site will obey this diagram. It doesn't matter if you're looking at if we're talking about ferropericlase or siderite. The energy level, their absorption spectra, will be governed by these diagrams. So this is why siderite can be used as a model for ferropericlase. So, but now let's take a look at how optical absorption works at high temperature. So this blue absorption spectrum was collected with the white laser method, with the new method that I have described. So, and the black spectra are the absorption spectra of siderite taken in a different run with a conventional optical setup. So you can clearly see that at 45 GPa, our absorption spectrum corresponds to the low spin siderite. But once we hit it to 12 or 1300 Kelvin, this intense absorption band is no longer present, and instead you have this weak feature that clearly tells us that we are looking at the high spin state at high temperature. So once we shut down the hidden laser and collect this absorption spectrum again, we see that the transformation at high temperature are completely reversible. So the absorption spectrum of our sample quenched after the of the quenched sample, it looks almost exactly the same as it did before we heated it. So which means that we're looking at so altogether, this means that we're looking at a reversible temperature-induced low to high spin transition, and then back to low spin transition after we shut down the hidden laser. So this is just a proof of concept that our new optical absorption system allows measuring absorption spectra at high temperature, and that these spectra can be used to say something about the spin state of the minerals we're looking at. Sure. Excuse me, can you speak up? We don't deal with it. Well, we collect thermal background separately, but at this low temperature, at 1200 and 1300 Kelvin, we essentially get zero thermal background because we're using a gated detector. Yeah, and our white laser is so much brighter than conventional light sources, so we don't have to worry about that. We do have to worry about that at higher temperatures, and this is the reason why this method is difficult to use at temperatures above 3000 Kelvin. But I will talk about that a little later. Right. Well, I will talk about that in a little while. But one of the good reasons to use siderite as a proof of concept is because its spin transition is so sharp at room temperature. So we can now play the same game with brigemanite and think of what minerals can be analogous to brigemanite in terms of their crystal structure. So a few words about the crystal structure of brigemanite. It has two iron sites, the larger dodecahedral site A and a smaller octahedral site B. These two sites can incorporate both Fe2 plus and Fe3 plus. However, the B site can incorporate Fe3 plus iron only. So there is no consensus on what is the spin state of brigemanite in the lower mantle. However, there is a theory-based view that it is only the Fe3 plus iron at the octahedral site that undergoes a spin transition at approximately 40 to 70 GPa. So what I want to say here is that this theory-based view actually provides us with a very nice testable hypothesis to deal with, to set up our experiments. But before we do that, we should know what are the optical signatures of low spin Fe3 plus. And to do that, we looked at other minerals that have Fe3 plus iron in at an octahedral site that undergoes a spin transition. And one example is NAL, and NAL simply stands for new luminous phase. So this mineral can incorporate iron also into two different sites. The octahedral B site incorporates exclusively Fe3 plus, which undergoes a spin transition at 40 GPa, as is documented by a Mossbauer study. So this mineral gives us a model for a spin transition in Fe3 plus sitting at an octahedral site, and therefore it may be used as a simplified model of brigemanite. So if we now just look at optical images of this NAL mineral as a function of pressure, we will see that at approximately 40 GPa, there is a pinkish tint appearing literally out of the blue to the color of this mineral at approximately 40 GPa. So this already, just as in siderite, this already tells us that something's going on with its crystals, with its electronic structure. And of course, this pinkish tint is recorded in the absorption spectrum. You can see that there is indeed a new band that appears at 40 GPa and intensifies up to approximately 50 GPa, and then it remains at with a constant intensity, more or less. So we can now plot this absorption band versus pressure, and here the different colored dots just show you compression and decompression data. You can see that the transformations we're looking at are completely reversible, which is in agreement with the spin transition scenario. We can also now, you can also ask me now, why do we expect to see a new absorption band that appears out of the blue in low spin NAL, in low spin Fe3 plus? And really the reason to that is because Fe3 plus has a very unique electronic structure, such that high spin Fe3 plus has 5d electrons that are spread among 5d orbitals. So there is no way you can excite one electron from one of the d orbitals to another d orbital, preserving the multiplicity, which basically means that there are no allowed absorption bands. But once you squeeze it into the low spin state, you mess up the electronic structure and you get allowed excited state. So in other words, the appearance of an absorption band is exactly what you would expect for low spin Fe3 plus. So when we can now do this, do high temperature measurements, and here the gray and black spectra show you the before and after heating spectra of NIL at 47 GPa. And you can see that you can use the area underneath this low spin Fe3 plus band to quantify the amount of the low spin fraction that you have at high temperature. So you can see that as you heat your sample, the area underneath this band continuously diminishes, which, in my opinion, records information on the amount of low spin fraction in the hot sample. So we can do that at several different pressures to construct spin state diagrams. And these are very unique because, as I said early, X-ray emission spectroscopy is not easy to combine with laser heating experiments, and therefore high temperature spin state diagrams that are constructed via experimental methods are very unique. And now we have a new tool that can allow for such diagrams. And here what you see is just the fraction of low spin in the NAL. So the blue color simply just tells you low spin, red color tells you high spin. We can now extrapolate this onto the whole lower mantle PT scale, and we will see that if the lower mantle was made of NAL, which it is not, we would have known its spin state by now, and only near the core mantle boundary would we get a pure low spin state. What I want to point out is that because crystal chemical similarities of NAL with bridgemanite and post-perovskite, it is possible that these two low mantle minerals have similar spin state diagrams. The second topic that I want to talk about is radiative thermal conductivity. Radiative thermal conductivity is one of the two microscopic heat transport mechanisms. The second one is lattice thermal conductivity. We know that radiative heat transport is an important mechanism in heating the surface of our planet by photons coming from the sun. But what we don't know is whether this is an important mechanism in transferring heat deep inside our planet, and that's what we want to figure out. However, there is a conventional view on what thermal conductivity is in the deep Earth. And here you can see the total thermal conductivity as a function of depth compared to the lattice and radiative components of total thermal conductivity. So an interesting thing happens in the thermal boundary layer, and this is the region that we're most interested in. Here you can see that radiative conductivity shoots up and lattice conductivity sort of goes down. So these opposite signs of change basically cancel each other out, and you end up having a total thermal conductivity that remains approximately unchanged. So what I want to say is that this total thermal conductivity is a very important quantity because it allows constraints on what is the heat transfer out of the core, what is the rate of heat extraction out of the core. And that energy value is very important for constraining geodynamic processes in the lower mantle because it provides energy for them. So the way we evaluate radiative thermal conductivity is in fact pretty complex, but what I want you to know is that radiative conductivity is inversely proportional to the absorption coefficient, which can be constrained by our optical absorption measurements. So what we actually measure is the total extinction coefficient, which is composed of the intrinsic absorption within the mineral on the electron levels of the mineral, plus scattering effects on grain boundaries or defects that you may have in your crystal. So this factor has been usually assumed equal to 0 because it's very difficult to constrain for diamond angle cells experiments. However, also radiative conductivity is proportional to the to temperature to the power of 4, which means that radiative conductivity is hugely sensitive to temperature. And this is the very reason why it sort of shoots up in the thermal boundary layer. So there are the conventional view of the radiative thermal conductivity is based on room temperature absorption measurements in diamond angle cells as a function of pressure. So you basically extract absorption coefficients, insert them in the K-rad formula, and you end up values of radiative conductivity as a function of depth. So there is a lot of disagreement, as you can see. But what these measurements agree upon is that radiative conductivity always increases with depth. So now we can do absorption measurements at high temperature. And here I'm showing you absorption spectra of post-perovskite before and after heating, the blue and black spectra. You can see that they are almost exactly the same. And the red spectrum is post-perovskite absorption at 2000 Kelvin. So we can see that there are some changes, but they're probably not very significant. And we can use this absorption spectrum to constrain radiative thermal conductivity at this pressure and temperature. And what probably, and the result tells us actually that room temperature measurements may be adequate in constraining radiative conductivity at temperatures below 2000 Kelvin. And this is just a model of radiative conductivity in D double prime, which is a very important layer in our planet. So we can now take this radiative conductivity model and combine it with what is known on lattice thermal conductivity to say something about the mineralogy of a low mantle. So I don't want to go into a lot of details here. I just want to point out that the combined model of thermal conductivity in the lowermost mantle is consistent with the fraction of post-perovskite being on the order of 70%. So this is one of the takeaway messages for you today. In order to sustain, so 70% of post-perovskite is needed to constrain, to have 13 terawatts heat of heat flux coming out of the core. So we, however, are not, restricted to doing measurements on just minerals. We can do measurements on rocks. And here I'm showing you absorption spectra of pyrrolite, which is a hypothetical rock that we think the mantle is made of. So here we're looking at the near-infrared range. The blue and black spectra are before-after heating. They look exactly the same, which is something you always want to have. And then you can see that at high temperature, the absorbance of this sample is very different. So the sample is much darker at high temperature. We can do similar measurements in the visible range. And these are completely different experimental setups. And we have to stitch the spectra together later on. So, but they do agree that in that high temperature sample is a lot more absorbing than it is at room temperature. So in here I'm showing you just absorption coefficients of pyrrolite as a function of pressure and temperature. So the bottom four spectra are approximate the PT conditions that are met on the Earth's geotherm. So these are the ideal, in a way, ideal conditions for, that we want to use, ideal input information that we want to use in order to constrain radiative conductivity as a function of depth. The red spectrum, however, that was taken at 134 GPa was taken at slightly lower temperature than we would expect for the core mantle boundary. So if we now run these spectra through the K-red formula, we end up with a radiative conductivity dependence that is opposite in sign in its depth, in its slope, compared to the conventional models. So this model, however, also assumes zero scattering in the sample, but we actually can say something about the scattering effects. And here I'm just showing you an optical image of our pyrrolite sample laser heated at 56 GPa. So we have extracted this sample, fibbed it, and then constructed TEM maps of its chemical composition and grain structure. So important things to note here is that our sample is essentially has three minerals: bridgemanite, ferropericlase, and a little bit of calcium perovskite, just as you would expect for the pyrolytic lower mantle. But the grain size, and that's very important, is on the order of, so this is 400 nanometers. So the grain size is actually comparable to the wavelength that we're using to probe the optical properties of the sample, which means that the scattering effects might be quite substantial. However, we can ask a question whether the optical absorption of pyrrolite can be explained simply by combining two hypothetical by just combining absorption spectra of single crystals where you would expect the scattering to be minimal. So if you do that, actually, you can come up with some sort of a scattering correction. And here is what I call single crystal model of radiative thermal conductivity. And again, to my big surprise, the difference between the scattering zero and the single crystal model is relatively small, probably within the experimental uncertainty anyway. But the important thing is that near the core mantle boundary, and this is the region where we want to know the radiative conductivity the most, its value is likely negligibly small. So one of the takeaway messages is that in geodynamic simulations, you can basically neglect radiative transport at all. However, we do want to study samples even at higher temperatures than 3000 Kelvin, and this is what we do for that. So we time our white lasers a little bit differently in these experiments. Now we have only 1 microsecond between the pulses. And we trigger the heating laser for just 1 microsecond. So we heat our sample for a millionth of a second. And in that time, its temperature shoots up to approximately 5,000 to 6,000 Kelvin, and then it cools off to approximately 3,000 Kelvin in a matter of a few microseconds. So and then it remains cold, essentially. So we collect this. So for these type of experiments, we're using a completely different detector, which is called a strict camera. So this is an example of a strict camera image. So what you see here are the supercontinuum pulses, the white laser pulses, as a function of time, how they traverse our sample. Here you can see that around the 8th microsecond, you see this big blob of thermal emission coming from the hot sample, just simply because the sample is hot during that time. And then the y-axis tells us something about the optical properties of our sample at such conditions. So basically, in just one shot, so we press fire, and everything happens instantly for us. So we get an image that looks like this, that contains information on the optical properties of our sample at low temperature, before laser heating, at high temperature from 6 to 3,000 Kelvin, and then as the sample is cold again. So we can now use this image to extract a bunch of information, and here is just integrated intensity over the wavelength range. So you can see that as your sample, as you wait till the heating laser arrives around the 8th microsecond, the sample remains quite transparent. Then the thermal radiation shoots up, but your supercontinuum pulses obviously have a much weaker intensity now, so which means that the sample is much darker at such high temperature conditions than it is at room temperature. And then you end up quenching your sample to a state that is more or less comparable to what you had before heating. So you can analyze these images in a different way, and I have to say that Nick has been of great help in providing a very clever way of how you can efficiently analyze such images for spectral information. And what you can see here is just an absorbance as a function of time, but the different colored circles show you the difference in absorbance at different wavelengths. So red is red wavelengths, blue is blue wavelengths. So you can see that before laser heating, the sample absorbs red light less than it does absorb the blue light. And at high temperature, that sort of gets messed up, but then you quench it again to a spectrum that has a positive slope and absorbs less of red light. So this, by the way, is a Bridgmanite sample with 6% iron at 117 GPa, shoot up to temperatures of about 5,000 Kelvin. And if we now extract absorption spectra out of here and compare them to the absorption spectrum of Bridgmanite of the same sample taken with a conventional absorption system, which is this gray spectrum, you can see that at high temperature you get an absorption spectrum that is very, very different from what you have at room temperature. And then as the sample cools off to approximately 4,000 Kelvin, this absorbance changes, but maybe not that drastically. The general shape remains the same. But then you change the temperature by only a few hundred degrees Kelvin downward, and you get an absorption spectrum that is very different from what you have at 4,000 Kelvin. And this is the temperature range where you would expect melting or crystallization for this mineral at this pressure. So in my opinion, what we're looking at is a change in optical properties that's related to the crystallization of Bridgmanite melt. And then again, you end up with a sample at around the 25th microsecond. You end up with a spectrum that is very comparable to what you had before laser heating. So, and this is another example. This is ferropericlase in D double prime at 135 GPa. So you can see that you barely have thermal background coming from your sample, but you do have a lot of absorption at around this time. So when the sample is hot, it essentially is very dark. So this instantly tells us that ferropericlase is extremely opaque at D double prime conditions, and also may have, and because it also has a spectrum to it, so you can see how it absorbs much less on the red wavelengths than it does on the blue, and that trend is also preserved at high temperature, which means that you basically get an absorption edge shifted into the near infrared range, and that must affect electrical properties of the mineral. So basically, ferropericlase exhibits a semiconducting-like behavior in this temperature range and at this pressure. So one instant conclusion that you can think of is that ferropericlase that, because it has such probably a much higher electrical conductivity at high temperature than it does at room temperature, it may govern the electromagnetic coupling of the core mantle and may be responsible for the transfer of Lorentz lines into the mantle. So I want to conclude by saying that although we have touched upon on probably the most important problems so far, there's a lot of things that need to be studied and looked at. And I'm really excited about the future of these methods here in GL and how in the next, and I really hope that in the next few years, these new techniques will allow us to to significantly advance our understanding of what's going on in the deep lower mantle. And finally, I want to say that this campus has been really great. So our high pressure results of our high pressure experiments may be inserted into various geodynamic models, which can also contribute, which can also take advantage of the seismic studies that are done here. And altogether, that will allow for a better understanding of what's going on in the deep Earth. So with that, I want to draw a few conclusions, which are simply optical spectroscopy is the choice to probe the spin state. I'm obviously biased, but I do think that that's the technique that will allow a better understanding of what's going on. Mantle rocks are at least 2 times more opaque at high temperature than they are just at high pressure at room temperature. Radiative conductivity is very small, probably negligible, and should not be used in geodynamic modeling. And finally, magma oceans are very dark simply because I have showed you that molten prismonite has a totally different absorbance than it has just at hot temperature. And with that, I would like to thank my collaborators, which have been of tremendous help. And with that, I'll take questions. Thank you. No, we don't. Probably 10 to 15 microns. So we assume that there is no temperature gradient across the height of the sample. So across the probed area that the temperature gradients are 0, we have to do that. We have no other way of computing them. Well, our sample is sandwiched between KCl wafers, which probably reduces the longitudinal temperature gradients in the diamond anvil cell. This is as much as I can tell you. Also, the sample is transparent, so it's mostly transparent for the hidden radiation. So, which means that that the hidden laser gets absorbed evenly throughout the thickness of your sample. So, and that probably would contribute to a more or less equal temperature conditions across the sample. We have, as I said, we have pressure mediums that basically shield our sample from the diamond anvils. And diamond anvils indeed may work as thermal sinks, but we shield our samples from the diamond anvils. So, so this is why we think that our samples remains at more or less constant temperature in axial direction. Well, you might be right. And we don't really know how refractive indices change as a function of temperature, right? But what is known on refractive indexes, on the variation of refractive indices at high temperature, tells us that this change is probably within maybe 10% of the nominal value. I would say so. So as a result, I would say that I would say that unlikely that is the change in refractive index would change the conclusions of this talk and the way we interpret our results. And also the evolution of absorption bands, their thermal evolution, tells us that it's consistent with what we would expect on their behavior at high temperature, such as broadening of like spectral broadening of DD absorption bands, or the redshift of the absorption edge.
What's the spot size of
It's so typically the white laser is smaller than the hidden laser. The hidden laser is about 15 microns across. The 15, and the white laser is about 5 microns. Well, the pinhole that we use collects all of the light transmitted through the sample. So the supercontinuum spot size is very small. So so I would say that the angular range that we have, the aperture that we have, is much larger than what we need to have for such measurements. Yeah, we have. So so far we have looked only at the change into the iron effect in ferropericlase, and what I can tell you now is that ferropericlase with 6% iron is a lot more transparent at corresponding temperatures than it is than ferropericlase with 13% iron. So so far I have looked only at two different ferropericlases. So say at 4,000 Kelvin, the 13% iron sample would be almost completely opaque, while the 6% sample would be semi-transparent. No, I wouldn't think so. And in fact, I'm actually not very optimistic about the use of this spin transition method, spin detecting method in application to ferropericlase, simply because once you hit ferropericlase, you usually see some sort of chemistry going on, even at low temperature, like 2,000 Kelvin. And we would want to study it, we would want to study ferropericlase somewhere in this temperature range. And so basically, what we always want to see is that the quenched spectrum looks exactly the same as the before heating spectrum, which is almost never the case for continuous heating of ferropericlase. So we could only study ferropericlase with the one-shot type experiments, the 1 microsecond heating. Well, but that's across the spot, but not along the heated spot. That's not along the probe direction, that's across the probe direction. And we don't see that in other samples. We don't see that in siderite. We don't see that in bridgemanite. We don't see that in NaL. So only ferropericlase shows this problematic behavior. And as you probably know, diffusion coefficients of ferropericlase, iron diffusion coefficients in ferropericlase very high simply because the crystal structure is so loose in a way. So, and this is why we can only study ferropericlase at very short time scales. I have actually tried loading ferropericlase into a coupler. Yes, right. So then that did provide some improvement, but that's a difficult loading overall. And yeah, I mean, a lot of work needs to be done here. And I'm not capable of doing all that work. We do have results on reflectivity, but those results are mostly on volatile systems such as nitrogen or hydrocarbons or water. And Nick actually has several projects on that. I don't know to what extent I can, talk here about what we have so far. But well, I think I can say at least that sometimes we do see reflecting behavior at hot temperature.
And say what you think seismologists should now look for or do with analytical models to deal with the required.
So what is shown here is the total thermal conductivity of bridgemanite pyrrolite of the mantle that contains exclusively bridgemanite, and here pyrrolite that contains exclusively postperovskite. So because postperovskite and bridgemanite have very contrasting lattice thermal conductivities, you would need you can actually model how much postperovskite you need in order to sustain the heat flow out of the core, because the heat flow depends, the value of heat flow depends on the total thermal conductivity that you have. So total thermal conductivity of the rock that's bridgemanite rich should be very different from that from postperovskite pyrrolite. So therefore, you can model how much, what is the thermal conductivity of these two hypothetical end members, what the postperovskite fraction should be in order to have the heat flow of 13 terawatts. And what these gray bars show you is the downward correction in lattice conductivity. So I have said that I'm combining my radiative conductivity model with lattice thermal conductivity model. But the lattice thermal conductivity model that I have is based on magnesium end member studies. So basically, iron-bearing bridgemanite hasn't been studied. Iron-bearing postperovskite hasn't been studied. So what is available on the data that's available in the literature is only on MgO or MgSiO3. So we know that if we insert iron or aluminum into these phases, their thermal conductivity should decrease. We don't know to what extent it should be suppressed, but we know that it should be there should be some effect. So this is why I have to introduce this downward correction factor. So when omega is 1, basically the correction factor is 0. So omega of 0.75 is a 25% downward correction factor. So this omega is more or less consistent with what we know on impurity scatterings in MgSiO3 from theoretical studies. So this may be the value that we would expect. That this is the downward correction that we would expect from molecular dynamic simulation. So basically, this value tells us that projecting this value on the 13 terawatts curve gives us the 70% amount of postperovskite. And the second part of your question was?
So what should seismologists look for to test your hypothesis?
I don't know. Right. Well, so I would say that cover the great amount of the comantle boundary. So only a relatively small fraction of the whole area has been covered by seismic studies. So we want to know more about what is. So that may covering the whole core will probably tell us more about what is the distribution of postperovskite along the boundary. So what are we changing again? Okay, 10 terawatts. Yeah, right. So you can only have, basically this means that you can only have a 13 terawatt heat flow for the downward correction that is smaller than 25%. We don't know what this downward correction, but if it is greater than 25%, you must have some amount of phosphorus at the least. Well, we're talking about 10 terawatts now. So, but for all heat flows that are greater than 10 terawatts, you must have at least some amount of phosphorus in order to have to sustain that heat flow. I would say that phase transitions take place faster than the time scale that we have in our experiments, but we haven't actually looked at any phase transitions with these methods yet, just melting. Well, if you have a sample in mind, we can certainly talk about that. And I would be curious about doing these kind of studies. But I'm just interested in the Earth material, so that's why I have looked at these targets so far. Yeah, absolutely. Well, yeah, so this is, here we can tune the PT conditions that we have to a more useful extent that it is possible in shockwave studies, right? So, and yeah, I also think so. And then, in shockwave experiments, they also often using light probes as means of probing what's going on with their samples. So we would have some direct overlap, not only in the PT, but also in the probe that we have for such conditions. So that'd be really great.